First of all, I would like to thank you for coming to this presentation. I will be talking about the lessons learned while trying to optimize smartphone GPU-based training. Starting with a bit of the introductions, I am Anish. I'm a master's student at the University of Cambridge, and I worked on this topic over the summer in Cecilia's lab, which is the Mobile Sensor Systems lab. I work closely with Young and Jagmohan during this process. Young is a PhD and Jagmohan was a postdoc at the University of Cambridge, who's moved to Southampton now. Getting into it, deep learning has been successful in many domains: computer vision, natural language processing, and edge computing. More importantly for us, deep learning on edge devices or resource-constrained devices the interest has grown quite a bit. And this is because there are many smartwatches and edge devices which come with features such as gesture recognition, voice recognition, and health monitoring. Here I am giving an example of a smartwatch, but many of these features, such as the voice recognition, can be found on smartphones as well. And personalization is at the core of all of this. Smartphones and these devices come with accelerators, heterogeneous accelerators, such as a GPU. Accelerators support SIMD operations, which is working on multiple data points, which is one instruction. And we wanna essentially be leveraging them for the training. One of the main challenges for deep learning on edge devices, as I've said, is the resource constraint. Inference using smartphone GPUs has reached the baseline for the CPU through many of the methods mentioned here, which are aimed at reducing the constraints, reducing the overall memory required or the overall computation required on the GPU. However, training on the GPU has been neglected. If training on the GPU were possible, we could leverage the heterogeneous hardware to address the need for personalization. And we could also lower the overall training latency, since the data no longer needs to be shipped up to a server farm for training. So in this paper, as I've said, we are investigating the feasibility of training on the GPU. There are quite a few deep learning libraries for resource-constrained devices, such as PyTorch or TensorFlow Lite, but these only include inference. They do not support training. Currently, MNN and CoreML, which is for Apple, support CPU for training, but our aim was to use the GPU. That's why we chose the MNN, because it's also not proprietary like CoreML. And we were only looking at fully connected MLPs, which will involve a matrix multiplication and then nonlinear activation. We started off by identifying bottlenecks that could be present and making our GPU slower. And before we move on to what we covered, it will help to cover a bit of the background of the next topic. First, let's look at the GPU architecture for Arduino GPU. The diagram is derived from the Arduino GPU OpenCL guide, but with some augmentations. The main takeaway here would be the structure of the GPU. It contains multiple shader processors, and each shader processor is built up of multiple ALUs and some shared memory. The diagram also maps well with the memory hierarchy in OpenCL. The private memory refers to memory in the form of registers available to each ALU, and this is very fast. Local memory is a shared memory present on each shared processor. Local memory is available to all of the ALUs. Then we have constant memory, which is a read-only type of memory. It can be present on the L1 cache or the L2 cache. The L1 cache is usually reserved for textures and such when the GPU is performing image tasks, graphical tasks. Then finally, the global memory is the slowest and largest memory, which is where most of our data will be stored, because it's a big matrix. Next, we shall look at the main parts of the OpenCL programming model. Work item is a thread that runs the kernel code. A work group is a set of work items that work in lockstep. The local size defines the number of work items in each work group, and the global size defines the total number of work items. We can now map these four elements onto our matrix multiplication case to help bridge the gap in understanding. And we will be doing so for a very naive kernel, which will take the ith row and the jth column of the two input matrices to then sequentially compute the output for the ij index in the output matrix. Each work item or thread will be assigned to one index in the output matrix, as explained before, ij. And the local size in this case is invariant because each work item is independent, but later on we'll see how it will also play a part. Finally, the global size will just be the two dimensions of the output matrix, the MNN, for example. Moving on from the naive kernel, we can apply some well-known optimizations, and we have listed the two which worked well together. First one being vectorization. As one would expect, we can transform the matrix from float to float fours, which is a data structure that acts like a vector in OpenCL, and a float four will just be a vector of dimension 4 with 4 floats in it. This leverages the hardware implementation of memory in computers. When we load a value, the neighboring values get loaded in as well, which are present on the cache line. And it's nice that OpenCL allows us to capitalize on this through vectorization. Finally, there's a secondary benefit of using vectorization, which leads to smaller work group sizes, as each work item is now responsible for multiple output indices. If you're using float 4, this would be 4 indices. Next, tiling. Up until now, we haven't talked about using the local memory, which is present on each shader processor. Reaching out to global memory every time to load a new value is very slow. Not only is it slow, but there will be tons of memory conflicts as well, as we are trying to look up a similar value from multiple kernels at the same time. With tiling, we will leverage the local memory, and what it means is each work item is responsible for loading in exactly one value from the sub matrices. For example, from the diagram we can see A11 and AB21. So one thread will be responsible for loading in one index from within this matrix, and then we will proceed to using the local memory to calculate the partial solution for C12. Once the matrix has been loaded, we can, since we're only looking at the local memory, the lookups are really fast. We also tried some other optimizations, such as more work per thread or prefetching, but our profiling experiment showed that vectorization and tiling outperform all of these. So for our experimental setup, we use 3 1+ phones, and over here they're represented in the order from oldest to newest. And we also use several timers that were available to us. So for example, a GPU timer, which is part of the OpenCL profiler, which helps to track the time a kernel is currently spent executing on the GPU. And finally, the timer tool from the MNN for the overall backpropagation step. So the first experiments that we did were related to the profiling of the matrix multiplication operation. We tested matrix multiplication on square matrices of size 32 to 512 and in steps of 32. We started off with some warm-up steps around 10 to 20, and then moved on to hot runs, and then the average runtime was averaged over these hot runs. For the 1+6 and 1+8, we can see that the GPU performs better than twice, whereas for the Nord, which has an older GPU, the CPU is almost as good as the optimized kernels. Next, we plug in our optimized kernel implementation with the CPU. We first experimented with 4 models as shown here. Surprisingly, model 2, which is deeper but much smaller than model 3, takes longer. Similarly, a shallower model, the shallower models 1 and 3 are faster than the deeper models 2 and 4, which points to the fact that the execution time is majorly affected by the depth of the model, which can only mean that the memory load operations required to load a new matrix into the GPU for the next layer is the major contributing factor in the execution time for the backward pass. Profiling, compute, and memory operations. Finally, given that we had some evidence that the backward propagation, that the depth of the models, the memory was the actual problem, we used the OpenCL profiler to see how much time was being spent on memory operations and the time that was being spent on computational operations, and we found that only about 9% of the time was spent on computation. Therefore, this essentially amounts to a very big bottleneck which we cannot overcome at this point in time. Therefore, in conclusion, we were able to identify 2 obstacles that can make the GPU faster. With optimization, we were able to make the GPU faster than the CPU and thus resolving the computational bottleneck. However, our experiments 2 and 3, show that the training latency on GPU remains much higher than the CPU. Thus, illustrating that the memory bottleneck is a very big issue that needs to be dealt. Though we have failed to accelerate the full training on GPU over CPU, our research findings could provide practical guidelines for further development of on-device training and better utilization of heterogeneous mobile processors with the CPU and GPU in the near future. And finally, I would like to focus on some of the future directions. Since our focus was only on accelerating matrix multiplication operations and thus enabling feed-forward network models, this work has not investigated convolutional neural networks. However, since the convolutional layers are computationally more expensive and thus fully connected layers, more computationally expensive than fully connected layers, we analyzing and improving the computationally expensive convolutional layers can be a potential direction for this sort of research. Our findings regarding the memory bottleneck issue could suggest investigating other memory optimizations, such as in the form of the model, the optimizer, or the activations, which can help alleviate some of the memory issues. Thank you.